In this video, let us learn to calculate specific heat capacity of the liquid by the method of mixtures applying half-time correction. Here is the experimental observations recorded. In this experiment, firstly we will weigh the empty calorimeter along with its stirrer, and its mass is noted here as M1 equal to 64.20 into 10 power minus 3 kilogram. Generally, in our laboratories, easily available liquids are water, kerosene, coconut oil. We used to find specific heat capacity for all these liquids, but in this particular experiment we have taken water. So we have filled the calorimeter of one third with water, and we weighed it. So it comes out to be M2 equal to 144.35 into 10 power minus 3 kilogram. And the calorimeter which we used is made out of copper, and the specific heat capacity of the material of the calorimeter is S1, which is equal to 385 joule per kilogram per Kelvin. Then the initial temperature of the calorimeter and liquid, that is the room temperature, is was noted as 30.9 degree centigrade. Then the aluminum solid which is taken in the Sinclair's heater is heated, and the maximum temperature it has attained is noted as final temperature of the hot solid theta 2 equal to 98 degrees centigrade. And this hot solid is then transferred to the copper calorimeter. Then it is stirred. After stirring, and the mass has been noted for the contents of the calorimeter along with the calorimeter, which is noted as M3. It is equal to 201.51 into 10 power minus 3 kilogram. So after adding the hot solid, a stopwatch, since we apply half-time correction, stopwatch will be switched on. Then hot solid, after adding the hot solid, we keep mixing. Then the maximum temperature, initial maximum temperature attained is noted as 38.8 degrees centigrade, that is theta 3 dash. And the hot solid which we used is aluminium, and the specific heat capacity of the solid S2 is 913 joule per kilogram per Kelvin. This is the specific heat capacity of aluminium. Then, so the time taken for attaining the maximum temperature is noted. For example, if it has taken 2 minutes to reach the maximum temperature, then half-time correction means what is the temperature drop for 1 minute. This I have explained for example. So for half-time correction, the d theta is 0.8 degrees centigrade. For the half the time, the drop in the temperature is about 0.8 degrees centigrade. Hence, the final corrected temperature or the radiation correction, whatever we call, theta 3 equal to theta 3 dash plus d theta. So theta 3 dash is nothing but it is the maximum temperature attained, that is 38.8 plus 0.8, it is 39.6 degrees centigrade. So this is the formula to calculate the specific heat capacity of the solid, and it goes like this: S is equal to M3 minus M2 into S2 into theta 2 minus theta 3, the whole thing divided by M2 minus M1 into theta 3 minus theta 1 minus M1 S1 divided by M2 minus M1 joule per kilogram per Kelvin. See, in this experiment I have converted all the masses into masses in kilogram, but I have not converted the temperature into Kelvin. Here the temperature in the numerator and the denominator gets cancelled. Even we do not convert it into one Kelvin, it will not make any difference. See here. Next, we are substituting all the values here. M3 equal to 201.51 into 10 power minus 3 and minus M2 144.35 into 10 power minus 3. S2, the specific heat capacity of the hot solid, it is 913 into 98, theta 2 is 98 minus theta 3 is 39.6. The whole thing is divided by 144.35 into 10 power minus 3 minus 64.20 into 10 power minus 3 into 39.6 minus 30.9 minus the value of M1 is 64.20 into 10 power minus 3 into 385 divided by 144.35 into 10 power minus 3 minus 64.20 into 10 power minus 3. See, in the numerator, in the first bracketed term, you could see 10 power minus 3 is common in both the terms. So, we can take this 10 power minus 3 outside. In the same way, in the denominator also, we have a 10 power minus 3 common in both first and second term. So, we are taking it outside. See, after taking these two 10 power minus 3 in the numerator and denominator, we have 201.51 minus 144.35 into 913 into 98 minus 39.6, the whole divided by 144.35 minus 64.20 into 39.6 minus 30.9. So, the 10 power minus 3 in the numerator and the denominator gets cancelled, minus 64.20 into 385, and the 10 power minus 3 in the denominator in the second term is also taken outside, it also gets cancelled. Upon simplifying, we get 57.16 in 913 into 58.4 divided by 80.15 into 8.7 minus 64.20 into 385 by 80.15. So, after multiplying all the numerators and denominators, we arrive at 3047725.47 whole divided by 697.31. Then the next factor is minus 24,717 divided by 80.15. Then when we divide the numerator by the denominator, in the first term we get 4,370.68 and the second term is 308.38. When you subtract the first term and second term, we get the specific heat capacity of the liquid is 4062.3 joule per kilogram per Kelvin. So, we can write our result as the specific heat capacity of the given liquid in brackets, it is water, is 4062.3 joule per kilogram per Kelvin. The standard the standard value for specific heat capacity of the water is 4200 joule per kilogram per Kelvin. The answer what we have got is almost closer to the standard value.